This section explains why a single object, the Lagrangian, generates the whole book. One object generates everything here, the Lagrangian. In Chapter 1, the words theory and Lagrangian mean the same thing. Its surprise is that interactions are not inserted by hand. Demand invariance under a local symmetry, and the force terms become inevitable, carried by gauge bosons whose strength a single charge fixes. That charge is simultaneously the conserved quantum number. Particles, forces, the whole catalog sit downstream of one choice, which symmetry you impose. The exchanged quanta picture is merely what relativity forces once. No signal outruns light. The chapter also draws a boundary. Masses alone escape the constraint. No theory generates them. They are measured input, and the Higgs is precisely what the symmetry could not supply. This section explains how a single scalar function encodes an entire physical theory, and how you read the physics off its terms. A theory is one scalar function. You write down the Lagrangian L, and the Euler-Lagrange machinery grinds out all the dynamics on its own. Maxwell's equations of motion themselves. 1/4 times F mu nu contracted with F upper mu nu, the wave equation falls out of 1/2 of the quantity, partial mu phi times partial upper mu phi minus m squared phi WR. Term type acts as a classifier. The kinetic term is universal, fixed by spin alone. The mass term is the m squared phi squared marker you learn to spot on sight. The interaction term, which is the potential energy part, is where every force actually lives. What selects the right L is invariance, both Lorentz invariance and gauge invariance, since the action must be a scalar. The whole method of the book sits right here. Write the invariant scalar, then read the physics off its terms. This section explains how gauge invariance turns a symmetry demand into a force. Start by demanding that a wave function's phase be choosable independently at every point in space, freely here, freely on the moon. Under that demand, the free Schrödinger equation breaks. The derivatives of the local phase call it chi, a function of position and time, no longer cancel, and leftover terms survive. Restoring the symmetry forces you to add a compensating field whose own transformation exactly absorbs those leftover terms. That field, being a 4-vector, is a spin 1 boson. It is the photon coupled universally to anything carrying the charge. The interaction is the price of insisting that a global freedom hold locally. This is Kane's move. Promote a symmetry from global to local, and electromagnetism materializes as the debt incurred. 3 such demands give 3 forces. Why these 3 unknown? This part explains how every fundamental force arises from one demand: local gauge invariance. Start from the idea that every force is the same debt. Pick an internal space where a particle carries a label. Proton versus neutron becomes an SU2 doublet. Then, demand that the orientation of that label be choosable independently at each point in spacetime. Once you make that demand, the derivative can no longer act cleanly. You must add a compensating field to repair it, and that field is the interaction itself. Kane runs this construction once on strong isospin, then declares the payoff, the covariant derivative, his equation, 4.18, is the main equation of the Standard Model. Non-abelian means the rotations do not commute. Because they do not commute, you need 1 gauge boson per generator. The group SUN gives n squared minus 1 of them, and the fields couple to themselves. Fix the coupling in one representation, and it is fixed for all. This section explains why the Dirac notation for spin takes the form it does. Demand a wave equation that is first order in time, which is the price of conserving probability, the Schrödinger way, and relativity forces it to be forced downstream of that single demand for linearity. The coefficients must then anti-commute exactly like the Pauli matrices, and no 2x2 set can satisfy that once mass enters, so the objects grow to 4x4 and the wave function becomes a 4-component spinor. The entire Dirac apparatus is the forced downstream of that single demand for linearity. The chapter hands you all of this as notation, something to read rather than something to labor over. Kane is explicit that you will never actually calculate with spin. The Feynman rules absorb it, and the transition rates fall out without it. You learn a language whose grammar was fixed by one constraint, and then you let it carry the fermions through the standard model. This section explains how a single recipe generates the observed world of particles and forces. Start with the free Dirac-Lagrangian and demand that 3 internal symmetries U1, SU2, and SU3 hold locally rather than globally. Once you make that demand, the ordinary derivative must become covariant. That single substitution, replacing the ordinary derivative with the covariant one, conjures every force carrier, the B, the 3 W bosons, and the 8 gluons, one for each generator. With them come every interaction. Particles then reduce to labels to how each fermion transforms under the 3 symmetries. The sharpest surprise is that the left-handed and right-handed components live in different SU2 multiplets, so parity violation falls out of the assignment itself, never put in by hand. Interactions are the price of local symmetry. This section explains why the particles you see in electroweak theory are not the fields the gauge symmetry writes down. The gauge Lagrangian hands you the wrong fields. What the symmetry group SU2 cross U1 writes down, the fields B mu and W3 mu, are not what nature exhibits. The photon and the Z boson are a rotation of that pair, fixed by a single demand. The massless combination must reproduce the electromagnetism you already know and leave the neutrino uncharged. That one constraint does 3 things. It diagonalizes the mixing. It pins the electric charge E, which equals G1 times G2, divided by the square root of the quantity G1 squared plus G2 squared. And it leaves exactly one thing. The theory cannot predict the angle of the rotation, the weak mixing angle, theta W, which you measure rather than derive. The pattern underneath is this. Physical particles are the eigenbasis of the gauge fields under a known boundary condition. Quantum chromodynamics is the same move performed on color. The gauge principle again, a new basis again, with self-coupling as the only new twist. This part explains where mass comes from in the Higgs mechanism, and why the mass is never something you write into the theory by hand. Mass is never written into the Lagrangian. It is read off the vacuum's arbitrary choice. Kane's whole chapter runs one move, climbed up a ladder of examples. Keep a symmetric Lagrangian. Flip mu squared to be negative so the potential's minimum leaves the origin. Then expand the field around one chosen minimum. Call it V. The excitation's mass is just the curvature of the potential at that point. In symbols, m squared equals 2 lambda times v squared. The symmetry still holds for the dynamics, only the ground state fails to share it. That is spontaneous breaking, and it is the same critical point structure as any Landau order parameter. The payoff, seated here, is this: gauge bosons interacting with such a vacuum acquire the W and Z masses that the Lagrangian forbade. This section explains how every number a particle physics experiment reports comes from one common object. Every number An experiment reports a cross-section, a decay rate, a lifetime is the same object seen through phase space. You start from the squared amplitude, written as the magnitude of m squared, which the Lagrangian hands you. You integrate it over the unobserved final momenta. Then you either divide by the incoming flux for scattering or you do not for decay. The chapter's quiet surprise is that width and lifetime are one quantity. Fourier rotated, give a state a complex energy E0 minus I times gamma over 2, and the single pole generates both the exponential decay in time and the Breit-Wigner peak in energy. So the lifetime tau equals h bar divided by gamma is forced, not fitted. Predict any standard model process by writing down m. The machinery here does the rest. This section explains how the W and Z bosons could be produced and measured once direct methods failed. A predicted resonance becomes a discovered particle only when you can make it at a countable rate, and a boson of roughly 100 GeV defeated the direct route, since electrons radiate away the energy you accelerate into them. Kane's move is to stop treating the proton as the projectile and treat it as a probability cloud of constituents. The observable cross-section then factorizes. It becomes the measured chance of finding a quark-carrying momentum fraction x, which is the structure function, convolved with the elementary quark-level cross-section that you can compute cleanly in the standard model cross-section that you can compute cleanly in the standard model. That product is the whole chapter. Once you hold it, you can predict every hadron collider yield yourself. The composite rate equals the probability of the constituent times the rate of the elementary process. The proton is an ensemble of colliders, not one. This section explains why measuring the standard model's free parameters is itself the sharpest test of the theory. A theory with free parameters cannot predict them. Experiment must hand them over, and the surprise is that pinning them down is already the sharpest test the theory can face. Unlinked interactions could scatter the value anywhere, even outside the interval from 0 to 1. Into every process that touches the ZW, into every process that touches the Z boson, neutrino scattering, electron-positron asymmetries, atomic parity violation in cesium. So measuring this one angle 8 independent ways and finding a single consistent value is overdetermination. Wong decay is the anchor. Its lifetime fixes the Fermi coupling GF, which equals G2 squared, divided by 8 times mw squared. That conversion turns a clock reading into the electroweak coupling. The chapter's move is to measure the inputs before predicting the outputs. Doing so quietly reveals that the redundancy of the measuring is itself the unification claim being tested. This section explains why an accelerator, before it tests any physics, already fixes which questions nature will answer. 4 numbers settle what physics is knowable: the beam particle, the final energy, the luminosity, and the useful fraction of that energy. The chapter's thesis sits deliberately ahead of any standard model test. The accelerator is a filter on which questions nature will answer, and you read that filter off the machine, not off the theory. Here is the generative pattern. Given a collider, you can predict its reach before any experiment runs. Energy sets the mass scale that the machine can probe. Luminosity buys event rate against cross-sections that fall as 1 over mass squared, so the two must climb together. Synchrotron loss scales as gamma to the 4th power, and that exiles electrons from circular rings, handing the energy frontier to protons. And because a machine takes a decade to build, today's committed facilities already determine the next decade's discoveries. This section explains what a particle detector really does and why detection is at bottom an act of selection. A detector is an inverse map. You never see the collision itself, only the few long-lived things that survive past about 10 to the minus 11th of a second, and you run momentum energy conservation backwards to reconstruct what was really produced squared 1 plus p2. The generative trick is that identity equals how a particle dies in matter. Hadrons shower on nuclei, electrons and photons radiate away fast, muons plow through iron, and neutrinos announce themselves only as missing momentum. Read the death signatures, invert them, and the parent mass. The chapter's real surprise is that the interesting event is one in about 10 to the 11th. So detection is really selection, triggering. What you build into the trigger's notion of interesting bounds, what you can ever discover. This section explains why the sharpest tests of the standard model are searches for processes it forbids. A theory's sharpest predictions are its zeros. The standard model lives naturally at about 100 giga-electron volts, so testing its high-energy structure demands tera-electron-volt colliders. But its exact conservation laws forbid whole classes of processes outright: separate electron, muon, and tau number, proton stability, and CP violation kept tiny. So the complementary probe is a forbidden channel rather than more energy. You measure a rate the standard model says is exactly zero, and any non-zero result is new physics against no theoretical flaw. It is a discovery with no background to subtract, unlike a bump hunted over an ordinary one. The muon G-2 sits 3 sigma off. The decay of the BS meson to a muon-antimuon pair is calculable at 1 loop. These are cheap experiments watching a null the collider cannot buy. This part explains how the object found at CERN was confirmed to be the Higgs boson rather than merely a new bump in the data. Identity here is not read off a label. It is reconstructed from behavior, since an object is what it does. A peak at 125 giga-electron volts is not yet the Higgs. The claim is earned by checking that one object simultaneously satisfies every prediction the Higgs mechanism forces: spin 0, even parity, a decay width near 4 mega-electron volts, and the Higgs mechanism forces. That mass proportionality was verified across 5 independent channels: the 2-photon channel, the WW channel, the ZZ channel, the BB bar channel, and the tau bar channel. The WW and ZZ channels do double duty. They confirm the field carries a vacuum expectation value, so electroweak symmetry is genuinely broken. Each channel is a separate constraint the same particle must pass. The mass itself, oddly precise and oddly light, becomes a signpost pointing beyond the standard model. This section explains why the search for smaller and smaller constituents stops at the fundamental particles of the standard model. There was a historical regress: molecule, then atom, then nucleus, then nucleon. Each object surrendered its structure once the probe's energy climbed near the object's own mass. Kane's chapter is that regress finally terminating. The measurement is electron-positron annihilation into a fermion-antifermion pair. You compare the results against a calculable point cross-section, which scales as the charge q squared times alpha squared divided by s. Every fermion, with the gauge bosons included, matches that point prediction with no form factor. The proton is the contrast. Being genuinely extended, it sits about 1 part in a billion below the point prediction. And that deficit is what operationalizes what structure even means. Point likeness then buys the whole edifice of field theory good all the way up to the Planck scale, with couplings that converge toward unification there. The chapter's primitive is this. Structure is a measurable departure from a computed point amplitude, and here the departure is 0. This section explains why quarks and gluons behave nothing like the electromagnetic case, and where confinement and jets come from. The whole chapter regenerates from a single difference. Photons carry no charge, but gluons carry the very color they mediate. That one fact drives everything that follows. Because gluons couple to themselves, the field between two quarks is squeezed into a flux tube of constant cross-section, so its energy grows linearly with separation instead of falling off with distance. Two corollaries fall straight out. First, colored things can never be isolated, and that is confinement. Second, a struck quark bleeds its growing field energy into pairs of pions as it flies, and that spray of particles is a jet. Given this, the question of which bound states exist reduces to which color combinations are singlets of the group. A quark and an antiquark form a meson. 3 quarks combined through the antisymmetric epsilon ijk, contracting Qi, Qj, and Qk, form a baryon. The final move is a substitution. Swap the group U1 for SU3. The machinery of atomic spectroscopy survives the swap intact, but baryons and color itself are genuinely new. This section explains why strong isospin is an accidental symmetry, exact looking only because a mass difference is too small to matter. A symmetry can be counterfeit. It can look exact even when no law forbids the difference it hides. It looks exact only because that difference is negligible against the scale that governs the dynamics. Strong isospin, the up-down interchangeability that once seeded the whole program of internal symmetries, is exactly this kind of counterfeit. Gluons are flavor blind. They cannot tell an up quark from a down quark. The two differ only in charge, and a mass gap of a few mega electron volts, tiny beside the roughly 250 mega electron volt QCD scale. Rotate up into down, and the strong physics is unchanged, the proton becomes a neutron, and no experiment notices. So the symmetry is an accident of the up quark and down quark mass difference being far smaller than the QCD scale. Its 1% breaking is direct evidence that the gluon coupling is flavor independent. This section explains why coupling strengths are not fixed numbers, but functions of how hard you probe. The fine structure constant is a function of probe scale that Habit quotes as a single number. Push more momentum into a scattering, probe shorter distances, and alpha grows. The mechanism is screeny. Virtual electron and positron pairs flicker out of the vacuum around a bare charge and orient like a dielectric, diluting the charge seen from far off. Approach closer, pierce the cloud, and you measure more. Every coupling runs this way, alpha 2 and alpha 3 as well, because every charge polarizes its own vacuum. The generative primitive is this: a constant is the asymptote of a screened field, and quantum loops are what give the vacuum a permittivity. This section explains what the 20 quark and lepton mixing angles actually measure. Nothing forces the quark states of definite mass to be the states the W boson couples to. There are 2 Hamiltonians, and no reason their eigenbases should coincide. They don't. That misalignment is the entire content of the chapter. A unitary rotation, V, the Kabibbo, Kobayashi, Muskawa matrix carries one basis into the other, and its off-diagonal entries are precisely what let a heavy quark shed its identity and decay. 0. The rotation and the strange and bottom quarks become stable. Kane opens on exactly that puzzle. A mixing angle, then, measures how far two natural bases of the same space sit apart. The Cabibbo angle of about 13 degrees says nearly, but not quite, aligned. Flavor change is basis, overlap, and the angles are its coordinates. This section explains why the difference between matter and antimatter comes down to a single number being allowed to go complex. Reality distinguishes matter from antimatter by a whisker, about 1 part in 1,000, and the whole effect reduces to whether a single number is allowed to be complex. Kane's thesis is that the Standard Model accommodates CP violation without requiring it. Charged current mixing rotates quarks through a matrix, call it V. You spend all of your phase. Redefinition freedom absorbing its excess phases, and the question is whether one phase survives. With two families, it never does. V can be made real, the Hamiltonian H stays real, and both time reversal and CP are exact. With three families, one irremovable phase remains. H goes complex, and CPT forces time reversal violation into CP violation. So the asymmetry between matter and antimatter is a counting fact. 3 is the smallest family number that leaves a phase standing. This part introduces the shape of all physics beyond the Standard Model, the map that chapters 23 through 26 will fill in. The Standard Model is a complete, effective theory of the visible, everything at the electroweak scale and nothing dark. Kane's move here is to give the whole territory beyond it one shape. Each anomaly is a new mass scale that the theory cannot generate from within. There are 5 of them. The hierarchy problem, which asks why the Higgs vacuum expectation value sits at 10 to the 2nd power rather than 10 to the 18th power GV. The strong CP, fine-tuning, neutrino masses, dark matter, and the matter antimatter, asymmetry. 5 doors, each opening onto a scale above the exymetry. The generative primitive is one law of quantum field theory. Every operator not forbidden by symmetry appears. So the dimension, 5 neutrino term, the theta term, and the Higgs self-corrections are all inevitable. A Standard Model's own consistency points past itself. This chapter is the index to chapters 23 through 26. This section explains grand unification, the idea that the Standard Model's free numbers stop being free once you embed its symmetry inside a larger one. Put the Standard Model's free numbers inside a bigger symmetry and they stop being free. They become theorems. That is the whole chapter. Embed all quarks and leptons of one generation into a single SU5 multiplet, and the tracelessness of its generators forces the charge of the anti-down quark to equal 1/3. Charge quantization is derived, not assumed. One gauge group means one coupling. So the 3 separately running couplings alpha must meet at a single unification mass of about 10 to the 17th power giga-electron volts, and the weak mixing angle, sine squared theta W, comes out fixed at 3/8 rather than measured. Here is the move. Every parameter you dissolve into a larger symmetry converts an input into a prediction. And predictions can be wrong, which is why grand unified theories are testable and, so far, mostly unconfirmed. This section explains why neutrino oscillation only ever measures a difference of masses. never a mass. A neutrino is prepared in one basis, flavor, which is what the weak interaction makes and reads. But it propagates in another basis, mass, which is the eigenbasis of free evolution. When the two bases sit at an angle and their components carry different phase velocities because the energy of each mass state depends on its mass, the superposition dephases. That interference is the whole signal. You never weigh a neutrino. You watch two mass states get out of step. So the observable is always the difference of squared masses, never a mass itself, a difference of squared frequencies. This is exactly how two detuned oscillators reveal only their beat, not their absolute pitch. This section explains dark matter as a quantity known only by subtraction. A galaxy spins wrong. Orbital speed stays flat as you move outward, when Newton demands it fall off as 1 over the square root of the radius. So the enclosed mass must keep growing out where no light lives, the mass rising in direct proportion to radius. That is an invisible halo inferred purely from what gravity requires, minus what actually shines. That subtraction is the definition. Dark matter is known only by a mismatch between the two, gravity's demand set against the visible light, and it is never seen directly. The chapter's real move is quieter. A particle proposed for entirely unrelated reasons, supersymmetry's lightest superpartner freezes out of the early universe. Run the leftover abundance arithmetic with plain electroweak coupling strengths, and it lands at about 25% of the cosmos, with no tuning at all. The candidate you already had gives the number you needed to explain. That coincidence is the whole argument. This section explains supersymmetry as a structural primitive. A symmetry is an operator that commutes with the dynamics while permuting states. Supersymmetry is the one whose generator carries spin 1/2, stepping across the boson to fermion divide. The generator, Q, acting on a boson state, returns a fermion state, the same way isospin steps from proton to neutron and back. Every quark, every lepton, every gauge boson gains a partner, identical, but for half a unit of spin. The symmetry must be broken. Were it unbroken, it would give superhydrogen and extra weak bosons, and none of these have been seen. Kane's deeper move is this. Once you posit the superpartner masses, the theory becomes fully predictive, every rate and every branching ratio calculable. The chapter's real subject is method. Supersymmetry stands as the worked example of the standard model turned into an instrument, for testing quantitatively whether any new physics is present.